lecture you can ask also. It is just revision, so just go through this revision so that we are now today we will inshallah start with the amplitude modulation, the first communication technique or the communication uh, procedures that are implemented in industry for communicating between distant points. So now I assume that my complex notation has the amplitude, has the phase, but they are time varying. All right. Now again I do the same thing. I will multiply my time varying complex number by a high frequency carrier EEJ 2 pi FCT. I take the real part. I will get the same thing. But here you can see that this X of C is now a time varying signal. Well, this is also a time varying signal, X of S, the in phase and the quadrature, the in phase and the quadrature component, in phase component and the quadrature component. So I've told you why it is called quadrature, because it is along the sine 2 pi FCT, which is orthogonal to cos, that is why in quadrature at 90 degrees, or in other words, orthogonal. As you could see that this signal will occupy a range of frequencies. Its bandwidth will not be zero. Okay. As you can see in the previous, when you just have the complex number, it was multiplied by cos 2 pi FCT. So cos 2 pi FCT is just an impulse at FC. If you want to find its bandwidth will be zero. But this bandwidth will not be zero. And because XC and XFS, you can see A of t is actually being multiplied. So this means actually this is being modulated and transferred to FC frequency. But as A of t is a slowly varying signal as compared to F of C, it will occupy a small bandwidth around F of C. Normally what happens that this FC is of the order, very much greater or more than 100 times the frequency of A of t. So this will occupy a small bandwidth around FC. These will be our in phase and quadrature components. They are the same, but now the amplitude and phase is time varying. This is a spectrum. You can see very well FC, and bandwidth is some bandwidth of the baseband signal. Whatever that bandwidth was is now totally around FC. Yes, XC and XX, the quadrature in phase, they are slowly varying signals or low frequency signals or low pass signals. This last representation is also used. You can also write your low pass signal as sum of the in phase component plus the sum plus imaginary of the quadrature, and this will be called the low pass equivalent of the band pass signal X of t was actually this signal on a carrier, and XFL is its low pass signal or low pass equivalent. You can also write this in phasor form. This is the magnitude of the phasor, and this will be the EJ theta, tan inverse y component over x component. You can also write it as follows. Here you can very well see it also looks like a quadrature, because we have definitely used a new representation of representing it in complex numbers. This will be the amplitude, this will be the phase, as you can see here, and this will be a low pass signal. So you could basically see previously this was also the low pass signal with respect to its time varying part. This was also low pass signal, but here it was represented in terms of cosines and then the real and imaginary. We just went to the cosine, the real part, then the cosine part, and then from the cosine we had the in phase and the quadrature. But here we are at the beginning using complex notation. So now you again multiply this with the high frequency carrier, you write it like this and you get the same representation. So there are different ways of representing the low pass and the band pass signals as we have just gone through. So this chapter is finished. Now we will go to the next chapter. If still someone has any question, he can ask before we go further. All right, this is amplitude modulation. Now we know that signals are analog in nature, or most of the sources they generate analog signals. Now, one thing is that you modulate or you transfer a signal to some higher frequency and transmit it directly. Or other method is that you do sampling and then you make it digital and then you apply digital modulation techniques. So here you will be considering totally on transmission through analog means, no digital transformation. So we all know speech signals, as I am saying some speech, music signals, images and video. They are examples of analog signals, and each signal has its bandwidth, its range, natures. For example, speech signal mostly is up to 4 kilohertz, and yes, speech signal is air pressure, and or the video signal it is some light intensity. If you have color video, then you have this red, green and blue components. Then another component for intensity, you also need to have audio signal for color TV broadcasts. So all these 4 signals or 5 signals need to be sent, 1 audio and 4 video. Analog signals, as I've told you, they will have different bandwidths. For example, speech has 4 kilohertz, music is up to 2 kilohertz, while video signals they occupy about 6 megahertz. So these are different forms of information that we are nowadays utilizing. Another trend, as I've told you, to digitally transmit analog signals, but still analog signal transmission is taking place, especially in broadcast situations. So broadcast means that there is one transmitter and it broadcasts its message to a number of receivers. All right. So in that case, for example, TV broadcasts, or we have audio broadcasts, radio stations, they still are using analog signal transmission. So this 3 and 4, this will treat analog signals by carrier modulation, and this performance of the system in the presence of noise, that will go into chapter 6. In chapter 5, we will be studying stochastic processes with respect to communications. So you will be able to understand noise, and then in chapter 6 you will be able to study 3, 4 and 5 combined together with respect to their system context. So here we will be emphasizing on analog signal and how do you modulate the signal with respect to amplitude, phase and frequency of the sinusoidal carrier, and then how you recover your actual information from the modulated carrier. This chapter will just devote itself to amplitude modulation systems, or AM systems. So where the message signals, they change the amplitude of the receiver. Chapter 4 will be for phase and frequency modulation system, where you will be changing the phase or frequency of the carrier. So first of all, we have modulation. So let us say I have a baseband signal, a low pass signal, m of t, which I told you will have a bandwidth around 0. This means that it will be 0 at all the frequencies which are greater than w. May those frequencies be positive, may those frequencies be negative. For negative, if they are less than minus w, it will be 0. For positive, if they are greater than w, it will be 0. So it is a low pass or a baseband signal having positive and negative frequencies. Now if I want to find the power, so this is a power signal, it is very long signal, it is a power signal. So what can I do about it? I will find its power, and this is the formula of power that we studied in the last chapter, as well as you have studied in your previous courses. So this is, the power. You integrate, you get energy, then you divide by time. As the time tends to infinity, you will actually get the average power. Now what happens that this M of t, or this message signal, this MT message signal, which is a low pass signal, is transmitted in the communication channel by impressing it on the carrier signal. So we will be seeing how it is impressed, but this is the carrier signal. The carrier signal is changed according to this MT. Maybe its amplitude is changed, or its frequency is changed, or its phase is changed. And then this changed or altered or modulated carrier is sent through the channel. This is amplitude, frequency, and phase. So here we are assuming that this phase at this point is 0, so that you just have AC cos 2 pi FCT. And the message signal modulates the carrier signal in either these three things: amplitude, frequency, or phase. And after modulation, the amplitude, frequency, or phase of the signal, it becomes a function of the message signal. So it will be changing it, and hence the output modulated signal depends on the message signal, how it has transformed the carrier signal. So we can say that in modulation, what happens that the message signal goes from low pass to band pass in the neighborhood of the carrier FC. So we will be seeing this in a while, how by the help of modulation, the signal, which was actually a low pass signal around 0 frequency, having negative and positive form, it is just transferred to f of c, the carrier frequency. So why we do this modulation? Various objectives are given. First objective is that you want to translate the frequency of the low pass signal to the band pass, or to the pass band channel, or band pass is also said, so both are right words. So because you know that each let us say TV broadcast, radio broadcast, or any other company and application is allocated a certain set of frequencies, a certain spectrum of frequencies of the overall frequencies, from the overall frequencies. So if you want, if I am, let us say I am a company, let us say, and I am using certain set of frequencies, so I will make sure that my frequencies, they only pass through that pass band or band pass which I have been allocated. So AM signals, they will go in the channel of AM. They will not be sent, let us say, through an FM band or through a 3G or a 2G band. Okay. That is why I need to transfer my information to the appropriate band. And this is done by the help of modulation. For example, you have microwave links, and now you know nowadays we have optical fibers, but still you have microwave links. You could see, let us say you're traveling out, or even in Lahore, you can see that you have two antennas that are directly connected with line of sight communication. So yeah, there's nothing, no object in between them. Yeah, line of sight, they are linked. So they are working at gigahertz frequencies. Now let us say my speech signal is only 4 kilohertz, but you know there are thousands of other users who are also communicating with one another through audio. So I will put all their signals in one channel, in one high frequency microwave link of, let us say of 1 gigahertz, which can accommodate a very large number of 4 kilohertz channels. All right. So, but I would need to transfer my 4 kilohertz channel. Let us say it is from minus 4 kilohertz to plus 4 kilohertz, around 0. But let us say it needs to be sent, just for sake of simplicity, let us say it needs to be sent at 2 gigahertz. So it will go up to 2 gigahertz. Other users will also be sitting around that time, around that frequencies, and hence they will all be sent over the channel. Second thing is also that Lower frequencies, they have larger wavelengths. Larger wavelengths means they will have large antenna requirements. If you know need to send those signals not through wire but through wireless, through through Maxwell's equations in free space. So in that case, you need those antenna structures who can transform the electromagnetic signals in the wire to free space electromagnetic waves. So their lengths, they roughly depend on the order of lambda, lambda over 2, lambda over 10, and something like that. But if you have lower frequency, you have very high lambda, and high lambda means you will need very large antenna structures. But if you take them to high frequencies, that will have small wavelength, and a small wavelength will require small antennas, which you can send by having less infrastructure cost. So this also simplifies the structure. You don't need a large structure to get the signal. Other thing is also frequency division multiplexing, which I actually also discussed here also. So here I was telling you that you transfer your signal to gigahertz, but why we are doing that? Because you want to send several messages. So you have a gigahertz bandwidth, and you can put several, you can multiplex several 4 kilohertz or 8 kilohertz channels in your gigahertz bandwidth waveguide or optical fiber. Something is also to have noise immunity. If you expand the bandwidth of the channel, this will be seeing in chapter 6. Then your system becomes more immune, or noise and interference immunity. Immune means it will not be affected by the noise if its bandwidth is expanded. That all the first 3 objectives will be met in this chapter. For fourth, that will be discussed mostly in chapter 6. He is mentioned chapter 4, but noisy channel, he will be discussing more of it in chapter 6. So this chapter is about AM, amplitude modulation, and there are several techniques. We will be comparing those modulation methods of AM with respect to their bandwidths and complexity. But again, their performance in noise will be discussed in chapter 6. So now comes amplitude modulation. Now in amplitude modulation, we have a message signal M of t. It is impressed on this carrier. The result is a new signal, which is actually dependent on MT as well as the carrier. And there are various ways of impressing MT on the amplitude, and each different way results in different spectral characteristics of the transmitted signal. We will describe these methods. These are 4 different methods: double sideband suppressed carrier, double sideband, single sideband, and vestigial sideband. So we go to double sideband suppressed carrier. What happens in double sideband suppressed carrier? Again, how do we impress? We multiply the message signal with the carrier. Simple multiplication is the method of impressing the message onto the carrier. So what is the modulated signal? It will be just message signal multiplied with carrier. So MT was a message signal, CT was a carrier AC cos. You have this simple multiplication and you are getting the modulated signal U of t. So you can see figure 3.1. This was a message signal, a low frequency signal. This was a carrier signal, a very high frequency signal. When they are multiplied, you will get this signal. Okay, this will be the double sideband suppressed carrier signal. You could see MT was a slowly varying signal. UT is a rapidly varying signal because of CT that contains high frequency components. But you could see that the modulated signal, it retains the properties of message signal. So that is why the message signal could be retrieved from the modulated signal at the receiver. You can see here, if this is a message signal, it has changed the carrier according to its own values. You could see here, this was increasing, decreasing, and then decreasing. Same thing you can see here is increasing, decreasing, and then decreasing. So that is important, that the modulated signal is dependent on the message signal. Now, how can I take the Fourier transform of my modulated signal, that is after multiplication? So we saw in in the last chapter, in this example. Adi Saro ko yaad hai this example? How do we got this? If m of f represents the Fourier transform of m of t, then multiplying this by a cos means you are multiplying by two exponentials. One exponential will take it to fc frequency, other exponential will take it to minus fc frequencies. Adi, does everyone remember this, or should I go to this example? Adi Salman sahab, Salman Jameel sahab, should I show that example? Is it enough?
सर मुझे तो याद है, मुझे बाकियों का नहीं पता.
अच्छा, चलो ठीक. Thank you very much. Are you roll number 144? Is this clear?
Yes, sir.
Thank you. So even if some students are not clear, they can see the example. Very simple, because once you multiply m of t by ej omega t, you can see in the Fourier, it takes m of f, its Fourier spectrum to fc. But here you will multiply, because each cosine contains two exponentials, one positive frequency and one negative exponential. So negative will actually advance this to minus fc. All right, you can see in that example. Acha. Figure 3.2. Yes, and you can see also here, this was the m of t signal. This actually I have shown you. This is new figure. This was m of f. This was a low pass, a baseband around zero frequency. It was occupying this much band, and this was its phase. So once you modulate, what happens? This total is shifted at fc. This total is shifted at minus fc, and its amplitude will now not be a, but it will be AC over 2. Why AC over 2 in Fourier? Because first of all, you are multiplying it with AC cos, so AC will come. Then cos is actually exponentials divided by 2, so it's divided by 2 factor will also come. All right, then the phases, they will be again translated to fc like this. Even if someone is not understanding, you can just tell me, so that we will go to this example. All right, so everyone has understood. Now let us go further. Now, so we could see that m of t has been translated by fc, but what has happened? The bandwidth is now 2w, whereas previously its bandwidth was w. This I had emphasized also before. If I ask you what is the bandwidth of this signal, you will say positive minus positive, highest positive minus least positive. This is w bandwidth. But once it goes into the pass band, or let us say to the band pass signal, what is its bandwidth? fc plus w minus fc plus w. This means its bandwidth is 2w. So you have made the bandwidth equal to double the bandwidth as was present for a low pass signal. Now here we have to understand some of the notions of our modulated signal, and all of it's written here. I've also highlighted, but let us just first read from the book, then I will also explain from the figure. Now all those frequencies, positive or negative, whose mod is greater than Fc, they will be called upper sideband, while all those frequencies which are less than Fc, they will be called the lower sideband, positive or negative mod. All right. So what this means here, that this set of frequencies greater than Fc, this one, and this set of frequency which is actually lower than minus Fc, but in terms of mod it is, you know, greater than Fc. This is the upper band. This is the upper of frequencies whose mod is greater than Fc is actually the upper band. And those frequencies which are less than Fc, a frequency's mod is less than Fc, or frequency mod is less than Fc. Okay, there is a mistake here. This will be minus Fc plus W. So you can clarify, this is minus Fc plus W. Right, this is minus Fc minus W. It's minus Fc minus W. So this frequency, which is actually greater than Fc in terms of its mod value. In terms of its mod value, it is actually less, but in terms of its negative value, it is greater. But we will be talking in terms of its mod value. In terms of mod value, Fc minus W mod, which is less than Fc, definitely. Here also minus Fc plus W, but its mod will be less than, you know, Fc mod. So these frequencies, they are the lower sideband, while these frequencies, they are the upper sideband. And you can also see the whole signal is actually present in the upper sideband, and then the whole signal is present in the lower sideband, because you can, this was the total spectrum which has been shifted at Fc. So this part which is higher, all right, and this part which is higher at this point, if you could see, this part was actually the positive frequency part from the baseband, and this part was actually the negative frequency of the baseband signal. So this baseband was shifted here, this same was shifted here. So this means that the upper sideband in effect contains the complete signal. Similarly, this part was actually came from here. This actually contained the negative frequencies of the low pass signal, and this part which actually came from here was containing the positive frequencies of the baseband signal. So again, the lower sideband also contains the complete information, the complete negative and positive frequencies of the baseband signal. आरी सबको समझ आ गया? Is this understood? I am not hearing any answers. Hari, Hamza साहब आप ही बता दें, CR साहब. Is this understood? All right. I am very surprised. No one is answering. हाँ जी, हाफिज मोहम्मद उमर, can you hear me?
Yes, sir.
अच्छा अच्छा, हाँ जी, कुछ समझ आ रहा है? Upper band and lower side band.
जी सर आ रहा है.
चलें, thank you very much. All right, so all of this is written here. So frequency content F greater than Fc corresponds to MF F greater than F0, and frequency content for F less than minus Fc, which means, you know, the negative part which is less than Fc, that will correspond to the frequency of F less than 0. So the negative component for upper sideband has gone to less than Fc, while the positive content of baseband for the upper sideband has gone to F greater than Fc. So the upper sideband contains all the frequencies. Similarly, you can see for the lower sideband. So that is why you can call this combined DSP suppressed carrier signal as double sideband, because it contains the total upper sideband as well as the lower sidebands, or the information is present with double its presence. That is why it's called double sideband. One thing is that it does not carries the carrier component. So the carrier was cos 2 pi fct, which it has two impulses at minus fc, one another impulse at plus fc. So that is not observable. You can see it is not present in the spectrum. And all the power was in the modulated MT. So you can see in the spectrum, you don't see any impulse of the carrier at minus fc or plus fc. You just see the empty spectrum, which is shifted at this frequency as well as at this frequency. So it is all present in the transformed M of t or modulated M of t. Yes. So there is no DC component. DC component means an impulse. So there is no impulse at fc. And if there was an additional carrier component, then there would be also a carrier at fc. But at this point, there is no carrier. That is why this signal is called double sideband previously, and it is also called suppressed carrier. So it is called a double sideband suppressed carrier. It has both the bands as well as the carrier is suppressed. Let's look at some examples. So this is a well-detailed example. Some steps are missing, which I will just explain. So again, this is the modulating signal, the message signal, the low pass signal, which is much less or more than 100 times less than the carrier signal. So we are to find that if I use double sideband suppressed carrier amplitude modulation, what will be the upper and lower sideband? It's very simple. It will be just multiplication, and multiplication will give me now two cosines. One is the carrier cosine, another is the message signal cosine. Again, some steps are missing, so I will switch to my notes. Again, simple multiplication. I just apply my cosine formula, angle formula, cos alpha plus beta plus cos alpha minus beta divided by 2 will give me cos alpha cos beta. All right, like this. Here I have done fm minus fc, but you can also write this as fc minus f1, because cos minus alpha is equal to cos alpha. Again, by applying the angles formula, cos alpha plus beta on 0 minus alpha, you will get cos alpha. So this is same, no problem. Now, what is the Fourier of this thing? The Fourier of this thing is an impulse at f minus fm plus fc, and then at f plus fm plus fc. Similarly, for this, it will be f minus fc minus f1, then f plus fc plus fn, as we have seen many times in the representation of a cosine. So we have four impulses, and if I draw them, so these two means that they are after fc, because this is f minus fm plus fc. So the impulse will be at fm plus fc. While this is fm plus fc, but there is a plus. This means this will be shifted actually minus into minus fm plus fc. This is at minus fm minus fm minus fc. This will be at minus fm fc, or you can say minus fc plus fm. So this thing and this thing, this is the upper sideband, right? And these two things, which will be fc minus fm, again this will be positive, and this will be, you can very well see, because this plus, this will be a negative. So fc minus fm positive, and then minus fc minus fm, this will be the negative. And this is actually the lower sideband. This is also the lower sideband. So this first will be the lower side, upper sideband. I'm sorry, this one will be the upper sideband, and this will be the lower sideband. In my notes, the this will be the upper sideband, while this will be the lower sideband. These two are lower and these two are upper. Their amplitudes are the same. AC A over 2 into 2, so AC A over 4. You can see it. This will be the lower sideband. Just take these two frequencies, lower to FC, and this will be the upper sideband. Take those two impulses which are greater than FC. Now, let us see the next example. Here M of t is a sink and you modulate to a carrier of 1 megahertz. Alright. So again, I have done this in my notes so that all the steps are there. So first of all, you have a sink. Alright. You apply the Fourier transform. So once you scale the time, then the opposite happens in the frequency. Even if you divide or multiply, always opposite thing will happen. If you are here multiplying, it will be division here. So f over this, and same amplitude will come here. It's mod, it's a positive number. This will be your frequency spectrum of this sink. Now how can you draw this? First of all, it is a rect. Rect of f is width is 1. But once you scale it by 10 to the power 4, this means its total width will come out to be 10 to the power 4. And this rect of f is present from negative to positive frequencies. So it will also be present from negative to positive frequency, but it's scaled with 10 to the power 4, which is 10 kilohertz. So it is equal on both the sides. This will be going from minus 5 kilohertz to plus 5 kilohertz. The height is 1 10 to the power 4. The height will remain the same as 1 over 10 to the power 4. Then let us say I impress my MT or my modulating signal, my low pass signal onto the high frequency carrier of 10 to the power 6 or megahertz. So what will happen? Actually, I am just multiplying the signal by 2 exponentials over 2. So one exponential will take it to 10 to the power 6, other exponential will take it to minus 10 to the power 6. The heights will be 10 to the power 4 or 10 to the power minus 4 divided by 2, because 1 over 2 will also come off this cosine. The widths will remain the same, 10 to the power 6, but here you can see the bandwidth is 10 kilohertz, while here the bandwidth was 5 kilohertz. Adi, everyone has understood? He is drawing all of those things. So this is the modulated signal, which sink into cos. It will look like a sink function in frequency domain. Its Fourier will be. This is the time domain signal. Sorry, this is a sink multiplied with a cosine. So you are just multiplying a cosine with the sink. This is a sink signal. So you can see the high frequencies of the cosine. They are being multiplied with this sink function or sink amplitude like envelope. Now, how can you find the power of your double sideband suppressed carrier signal? So again, the formula is the same. You take the modulated signal, use the power formula, and you will get the power. So what is my modulated signal? This is this thing for double sideband suppressed carrier. And I can open this up. Cos square will become 1 plus cos 4, a double angle formula over 2. 2 and AC, they come out. Now m square t, this will be as it is, but m square into cos 4 pi f c, this will become 0. M square into cos 4 pi f c t, and then integrated over this whole time divided by time, this will come out to be 0. You will just have m square dt, the first term, and this is actually the power of the message signal. So the power of the modulated signal comes out to be AC square over 2 into the power of the message signal. Again, why this product will be 0? Because you can see that m square is a slowly varying channel, while cos 4 pi is a very high with very high frequency, a very rapidly changing signal. So in effect, what is happening that its equivalent positive and negative cycles will be coming in one single constant amplitude of mt. They will be actually cancelling m of t. So m of t cos 4 pi fc will go 0. This is also shown in the figure. This is your x of t. Sorry. This is your m square cos 2 pi 4 fct, and here he is showing that this and this, they are both opposite. Similarly, this and this are opposite. Reason is that you have a very high frequency cosine multiplied by a slowly varying m of t. So you will have equal positive and negatives, and they will cancel. Even if they do not cancel, there are a small value, but a very small value will be there. Then small value divided by t, as t tends to infinity, will definitely make it tend towards 0, almost 0. Now let us find the power in the modulated signal and the power in each of the side bands in the first example that we studied. So in the first example, we know m of t was a cos 2 pi fct. So what will be its power? Again, its power was seen in the previous chapter 2. Power of a cosine to be just a square over 2. Alright. This is a power signal. You can again apply the same formula. This will become, cos mt square, a square, cos square. Cos square will be 1 plus cos 4 over 2. Cos 4 will go away in one time period, will be 0. So again, you will get a square over 2. So a square over 2 is the power of your message signal. And we know that the power of the modulated signal is AC square over 2 into the power of the modulating signal, which was a square over 2. So this will be the power of your modulated signal. So because this is the power of the total signal, so the power in the upper and side bonds, because they are equal signals or they are symmetric, you can just divide by 2. So AC square, a square over 8 will be the power of the upper side band. Similarly, that will be the same power of the lower side band, like this. Are there any questions you can ask before we go forward? The second thing is demodulation. How can you get back your original low pass baseband signal from this modulated DSB-SC signal? So at this time, we assume that there is no channel distortion, there is no noise. Whatever the signal was sent is received at the receiver. So the signal received at the receiver is now mt into cos 2 pi fct. But actually, I want to get back this m of t. So how can I do that? What I do, I multiply my received signal by a locally generated cosine. This locally generated cosine, it could be generated by a local oscillator. So it will have certain phase shift with respect to the incoming cosine inside my modulated signal. There will be some phase shift. And we multiply this, and then we multiply this, we get a product, and we pass the product to a low pass filter with a bandwidth of W. So I have done this multiplication, and this is my locally generated cosine, and this was my received signal. So received signal, is AC mt cos 2 pi fct. It is just, this is a received signal multiplied by a cosine. Again, you can apply the cosine formula, cos alpha plus beta and plus cos alpha minus beta. So cos alpha plus beta will give me 4 fct plus phi. while cos alpha minus beta, you know, this 2 cancel will just give me cos phi. So you will be getting these two signals, and its spectrum is also shown in figure 3.7. So you have a cosine at 4fc, so it will have matlab, cosine at 4 pi fc. In other words, signal is present at 2fc, another signal is present at 2fc, but you also have a plus signal which is a low pass signal, which was m of t. So you still have that modulated signal, but this has gone now to 2fc, as well as the low pass version, or the signal that we want, is also now present as a result of this multiplication. Now we needed just the message signal, which has a bandwidth of W, which is totally present here. So I will just apply a low pass filter. It will just pass this much signal, while these two signals will be rejected by the low pass filter. Hence I will get back my original baseband low pass or low pass signal. Apply low pass filter centered around 2fc, centered around 0. So the signal component at 2fc will be eliminated. So low pass filter is also, this is a low pass filter, it will just pass the lower frequencies. So after the low pass filter, you know, this will go 0. You will just get this part, this signal will be received. Now here you can see that we are receiving our m of t, but you know, m of t is being multiplied by cos pi. So its amplitude will be reduced by cos phi. If phi is 0, then you know there is no reduction. But what if phi is 45? So you know, in case of phi 45, this will become 1 over 2 under root. So amplitude will decrease by 1 over 2 under root, and power will be half. And if, let us say phi is 90 degrees, and you know, cos 90 is 0, then you won't get the low pass signal. So this gives an other requirement, and that requirement is that phase must be 0. And for that condition, we need a phase coherent or synchronous demodulator. That is, the phase of the locally generated sunlight should ideally be 0. With respect to the received signal, they are both in phase, they are both phase coherent, they are both synchronous, they are synchronized. Okay. So you know what is the phase of your received signal, and you generate the local carrier or the local cost of C with the same phase as the phase is present in the received signal. So this is called phase lock. So the sinusoid is phase locked to the phase of the received carrier. Now how can this be done? This can be done in two different ways. One method is to add a carrier component into the transmitted signal, as shown in figure 3.8. We call this the pilot tone. Its amplitude is AP, so power will be AP square over 2, because it will be AP some cosine. And we keep its power to be very much smaller, or significantly smaller than those of the modulated signal. So this is a transmitted signal, double sideband, but is no more suppressed carrier. You also are sending the carrier. So what we do here, we have the master signal, you multiply this with the carrier. This is your double sideband suppressed carrier signal here. But what you do, you have this carrier, you make its amplitude smaller, and then you also add this carrier with the already double sideband suppressed carrier signal plus carrier. So it will be double sideband with the carrier. It will no longer be suppressed carrier. All right. And here we normally keep this power of this carrier to be low as compared to the power of the modulated signal. Now what will happen at the receive signal? Once the receive signal is received at the receiver, so you take the receive signal, you pass it to a narrowband filter. You know narrowband filter? It is a narrowband filter at around some frequency. So you have a narrowband filter at FC. So what you will do? It will just take out the FC carrier from the combined signal. So you will it will be of this it will be generated from the same receive signal. So this will now act as your locally generated oscillator carrier. You will again multiply that low pass filter. You will get back your MT with cos phi 1 or phi is equal to 0 with synchronized oscillator with respect to the receive signal. So you could see here alright, this also point is there that here you have the receive signal synchronized and you are carry you multiply low pass filter, but in the low pass filter you have M of t, but you will also have the DC signal. Because remember, now this signal once multiply, it will pass to low pass filter. You will be getting this signal, but this signal will also have the receive, will also have the carrier. Because remember, now what will be happening? That you will also have a carrier here that will pass through the low pass filter. So you can carrier, you can say low pass DC spectrum. You have a DC signal at 0 frequency that will also pass through the low pass filter. Because remember that now the original signal had a carrier also, so it will be coming everywhere, but these will be neglected by the low pass carrier, but this will be passed by the low pass filters. There will be a carrier also at its center. So that you can get rid of that carrier by, let us say, putting a capacitor which will block the DC part. So you will get back the original M of t. So it needs to be subtracted or it needs to be taken out. That DC component needs to be taken out in order to recover your M of t. But you can see the drawback here that you have to allocate certain power of your signal power to the pilot or to this low magnitude additive pilot signal. Another thing is that you can also generate a phase locked sinusoidal carrier from the received signal without the need of a pilot signal. So you can also get back your sinusoidal signal of the same phase as the phase of the incoming received signal without the need of a pilot signal by the use of a phase lock loop. This will be studied in the next chapter. More details are given in section 8, and you will be also doing some of its experiments in labs to understand its functioning, the phase lock loop. So any questions you can ask before we go further? All right. So conventional amplitude modulation. This is a different type of AM modulation And what is the difference with respect to the previous DSB-SC double sideband suppressed carrier is that you have a large carrier. There you were adding a carrier, let us say at the later phase when we said how to get back, phase lock carrier, then we had additional pilots, but that was a pilot signal and it had a very small amplitude as compared to the modulated signal. But here this is the opposite. You have a very large carrier component. In addition to the DSP signal, you have a very large carrier component, not a small or a zero carrier, but you have a but which is also very large in comparison to your modulated signal. That is why it is a different type of amplitude modulation. It is called conventional amplitude modulation or simply double sideband AM. It is double sideband AM without any suppressed carrier. But normally it is called conventional because in order to tell us that it has a very large carrier. So it is mathematically represented as follows. So we have m of t plus 1 AC cos 2 pi FCT. So actually what is happening, you could see if you alright, but we can just see from here, this will be AC cos 2 pi FCT and the signal will be AC MT cos 2 pi FCT. You can see that AC MT cos 2 pi FCT is the same as a double sideband, but you have another signal AC cos 2 pi FCT. Okay, and we make sure that the AC cos 2 pi FCT is large in comparison to AC MT cos 2 pi FCT. And how this is done, this will be explained as follows. Here we make sure that this MT is less than or equal to 1. Normally it is less than 1, but in general it is less than or equal to 1. So this MT is less than or equal to 1. So it is a changing signal with time, but its mod amplitude will always remain less than or equal to 1. This part is a DSB-AM signal, while this part is the carrier, and this denotes its time domain signal. This how this will look like, and these signals you also be seeing in the lab. Nowadays we don't have those hardware labs, but you'll be doing this in through piecewise the software. You will be seeing this. So why we are putting this large carrier? Because you will see this will help us in simplifying the structure of the receiver or the demodulator, and this will actually make the receiver cheaper. So that is why commercial AM radio broadcast employs this conventional amplitude modulation, where you have a very large carrier with respect to the signal M of t. As long as this MT is less than or equal to 1, then you can very well see that 1 plus MT will always be a positive number, because at the maximum this MT, this will be minus 1. In that case this will be 0. Alright, so your envelope will actually just come here to be 0, but still it will remain positive. In case, for example, if I say that my MT is not less than 1, let us say it is greater than 1, and similarly in other words MT is less than, it is minus 2, then you have a problem, because 1 minus 2, this will become minus 1, and you can see that your signal will actually go negative. From positive it will go negative. That is called an over-modulated AM signal, and in that case your modulation becomes complex. So that is why we actually always use techniques to make this MT much smaller as compared to 1, so that we never approach this condition, or even we don't approach MT is equal to 1. We are always less than 1 in terms of mod, so that the envelope always remains positive. This envelope doesn't go here, but this envelope doesn't go up. Alright, so there's no reversal of signs. How can we make sure that MT is always positive? Matlab is always much less than 1. So what we do, we say that M of t is represented as A times MNT, where MNT is a normalized form of MT. You know, where MNT is MT divided by maximum of MT. This means now my MNT will be at the max between -1 and +1, because you have divided it by its maximum. Its maximum might be 100, but once you divide it by 100, the maximum point will become +1, or the minimum minus point will become, let us say, if it's also -100, after division by 100 will become -1. So your signal will be restrained between -1 and 1. But again, in -1 and 1, the problem is that when you do 1 plus MT of this MNT signal, then you can very well see again you will be having those points which will go 0. But we don't even want to go to those zeros points. So what we do, we multiply this MNT by a scaling factor A, which is again less than 1. So this is going up to 1, this MNT, 1 minus 1, in between 1 minus 1. But on multiplying your MNT by A, this will, A is always less than 1. So 1 minus 1 into a number less than 1 will mean the number will now be further restrained to some more smaller number. Let us say 0.7, minus 0.7 to plus 0.7. It will be more smaller or less, its mod will be more less than 1. You can also say that MNT will now become less than 1 and A is between 0 and 1. Alright. So in that case, you can see that AM and T is always less than 1, positive or negative. So this means this value will always be greater than 0. Okay. If Mn is positive, then A is always positive. So this will be a number greater than 0 but less than 1. So this number will be get positive. Even if MNT is negative, but will be less than -1, or you can say in terms of mod greater than less than -1, or in terms of mod, but where in terms of numbers it will be greater than -1, so it will be -0.9, -0.8 or something like that. This AMN term total. Alright. So this term added with 1 plus, it will again get a number which will be greater than 0. So the whole signal will be above 0. This will be your modulated signal, where you will make sure that 1 is much greater than or greater than AMNT. Hence 1 plus AMNT is always greater than 0. So if you are asked in exam many times, these questions have come to make up your double sideband, conventional double sideband signal, or double sideband for broadcast, or double sideband. Simple double sideband is also this signal, okay, where they ask you that there should be no over modulation. In that case, you will make sure that AMNT is is less than 1. Now, what will be the spectrum? So the spectrum, you can very well see it will be two signals. One is the carrier and the other is the modulated signal, which is again on making sure that AMNT is less than 1. This cosine will give you 2 pulses. This cosine will shift the baseband signal at F and FC. The baseband signal is Fourier transform, but after modulation, you not only have this double sideband suppressed carrier, but also you have the carrier. Alright, so you can see this information here. And you can also see the amplitude here. This is AC over 2 and this will be ACA over 2. This will be definitely less than AC over 2 because A is a factor which is less than 1. That is why these are smaller as compared to the spikes which are of larger value. Twice bandwidth that you can verify. If you have time, you can do this assembly. First of all, I will take your attendance. If you have any questions, you can ask. Otherwise, I will cover, 5 minutes. I will cover more of this lecture. All right. No questions. So let us go further. Now, again, assume that this is your modulating signal, and then you have a carrier which is much greater. You have to find the double sideband AM. It is not suppressed carrier, so you have to just find DSB AM, assuming a modulation index of A. So A is the index which we know it will be always between less than 1 or between 0 and 1. You can see here the value of A is between 0 and 1, positive value, and less than 1, greater than 0. This will ensure that the spectrum is never over modulated. Signal is never over modulated. This is my double sideband signal, double sideband conventional AM signal, carrier, and this is MT into A. Again, I find spectrum. So cos 2 pi FC will give me cos 2 pi FCT, and this will give me 2 cosines. Then you can write those cosines as lower sideband, as upper sideband, as we did in the last example, first example, where we wrote these 2 cosines in terms of their additive and subtractive components. This will be the lower sideband, this will be the upper sideband, and you can see their values. I write their Fourier spectra. So this will be EJ, this will give me AC over 2, 1 over 2 from cosine, and you have 1 EJ at FC, there is minus AGFC, so you will have del F at FC, and FC minus FC, you will have 2 spikes. This will also have 2 spikes. These are lower band spikes, less than FC. This will also have 2 spikes, but they will be greater than FC in terms of their mod values. This we have actually done this already. We have done this much part, and this much part is from the cosine, and you can very well see this part comes from the lower sideband. This part comes from the upper sideband. So this was the upper sideband. If I form its cosine, the cosine is EJ over 2. This means it is ACA over 4. For all these terms, the magnitude is ACA over 4 into del of respective frequencies. So these are the dels, and this is ACA over 4. So I hope this is also understood. Now if I draw its magnitude, so the magnetic spectrum is shown in figure 3.12. You can see this. So we have the lower and upper sideband, but we also have these carriers, which were actually not present in double sideband suppressed carrier signals. Now if I find the power, so you should remember what was how could we find the power? So power was found by taking square of the frequency components, as we've seen in the last chapter. So this becomes the power of that component, and you sum all the powers, you will get the total power. So if I've asked you what is the power of the carrier, so you will say, sir, it is AC square over 4 of 1. There is also AC square over 4. So total power will be AC square over 2. So AC square over 2 is the power in the carrier. if I ask you what is the power in the in the the modulated signal, so you have AC A over 4 square, this will become AC square A square over 16. But this is also present in positive and negative lower sideband frequency. This will become AC square A square over 16 into 2. This will become AC square A square over 8. All right. All right. And this will also become AC square A square over 8. But when you will add both of them, it will again come out to be AC square A square over 4. So you can just compare this power and this power. So you can see this power is much greater as compared to this power. All right, because first of all you have 2 here, you have 4 in the denominator, then you have A square which is less than 1 as compared to there's no A square here. So again you can see that the power in the carrier is greater than the power in the combined two sidebands. All the time is up. If you have any question, you can ask. I will be ending the lecture.